Okay, so the record is started. So Miyato-san, please, can you make the opening?
Oh.
No. Opening is Nakajima-san.
Yeah, my bad. You're right.
Okay. So, okay. So, this is Nakajima speaking. As you see, this is, I think, a second IFERC workshop on GPU programming. Okay. And today, we have 4 presentations and discussion time. And especially we will have the 2 talks which are related to the Fugaku supercomputer. Okay. One of them is the experience feedback on Fugaku supercomputer. I think this is related to the computing in terms of the MPI library. And the other one is the gyrokinetic simulations of multi-scale turbulence on the supercomputer Fugaku. In this case, I think some results which are related to the productive run will be presented. And although, of course, we have 2 other talks. Then I expect that this workshop will encourage the utilization of the GPU and the other the architectures like a Fugaku and so on. Okay. And so finally, I'd like to say thank you very much for attending the meeting and also presenting talks. Okay, it's a very short talk, but thank you very much again. And let's start our workshop. Thank you.
Thank you very much, Nakajima-san. So the first speaker is Siri. Siri, I will give you the right to share your screen.
Hello, France. Hello.
Okay. Now you can start, Siri.
Okay. So can you see my presentation?
We can see your screen, but it seems like it's your office.
Strange. One moment, I will try to share it again. And now?
Yes, we can see the presentation.
Okay. So hello, France. Good morning, everybody. Good afternoon, colleagues from Japan. My name is Serhiy Machalsky, and today I would like to present my experience feedback on Fugaku supercomputer. As you maybe know, Fugaku supercomputer is a #1 system on top 500 list. It's located in Riken Center for Computer Science in Kobe, Japan. The system was launched in June 2020 and official production phase started in 2021. The Fugaku supercomputer is the first system with theoretical peak performance of 0.5 exaflops. So we are really going towards the exascale supercomputer. The high-performance Linpack benchmark, which is used to calculate the supercomputer ranking in top 500 list, provided 442 petaflops of the peak performance of Fugaku supercomputer, which made this supercomputer already second-time system #1 in top 500 list of the supercomputers. In today's talk, I will always compare Fugaku supercomputer with the Marconi Skylake partition, as typically used for our plasma physics community here in Europe. Here in the figure, you can see the schematic view of one compute node of Fugaku supercomputer, which was made by Fujitsu company based on ARM architecture with the code name A64FX. One very important difference and direct difference in comparison to our typical Intel computing node is that Fugaku compute node consists of 4 sockets, what they call it core memory groups. For me, it's socket. A typical Intel node consists of two sockets. For last, let's say, 10 years, we were working mostly on the two sockets hardware. Another important difference here is that one such a socket or core memory group consists of 13 cores. However, only 12 of them are compute cores. Another one, the last one, is a core which is reserved for the system needs. And we know from our previous projects that system during the computation always makes some tiny interrupt. In most of the cases, this interrupt doesn't affect at all computation, but sometimes they could interrupt our computational. So in my opinion, it was very nice novelty here to sum all these interrupts on the system cores. In total, we have, as I announced, 4 sockets with 12 compute cores per socket. So in total, we have 48 compute cores per one compute node, the same as on Marconi SKL partition, 48 compute cores. We also have typically base CPU frequency on both hardware, so they produce the same, very similar peak performance. Another very important difference, and I think it's the main improvement or main introduction in the Fugaku compute node, is the different structure of the main memory. Fugaku compute node is equipped with so-called high bandwidth memory second generation. And as you guess from its name, it has very high bandwidth. One memory block has 256 gigabyte per second of the memory bandwidth. So in total, 4 blocks provide 1024 gigabyte per second of the main memory bandwidth. And it's really huge. In comparison, Marconi scale partition has maximum theoretical memory bandwidth 255 gigabytes per second. However, such high memory bandwidth has one very important disadvantage. It's the memory capacity. One memory block has only 8 gigabyte of the memory capacity. So in total, we have 32 gigabyte of the memory. However, this memory is not fully available to the users. 5 gigabyte is used for the system needs. So the user can have access only to 27 gigabyte of the main memory, which could be really restriction for some of the production application when the memory is a problem. For example, on Marconi scale supercomputer, the capacity of main memory inside one computing node is more than 180 gigabyte. Also here we have different inter and intranode networks in comparison to the Marconi scale partition, about which I will talk later on. In order to get project running on Fugaku, it took us quite significant number of weeks. However, was surprisingly for us, in order to open account on the supercomputer, it took us more than 6 weeks. We needed to open different user account, user certificate, and finally account for the supercomputer. And we sent several mails by real post back from Germany to Japan back and forth. But finally, 12th of January, we opened our accounts and we could start, we thought, our test. However, we realized that the Fugaku supercomputer was in very long maintenance, which is represented here in the calendar heat map, which yellow color represents when the Fugaku supercomputer was in maintenance. Red color stands when system had a problem and compute nodes were not available. And green color represent when we had normal operation day. Our project ended at the end of March, and you can see that most of the time system was in maintenance, and we had many days when system didn't work at all. However, such a result didn't really surprise us, because we knew such a things, some interrupts, problems, issue happens always with a new supercomputer, especially when it's the biggest system in the world, such large as Fugaku, and on top of it, when it's based on some new hardware, like it is Fugaku supercomputer. So in total, we didn't have so many regular operation days to fulfill all our tests what we planned. However, most of them were done, which I would like to show you today. Let's start with the first benchmark that I would like to present is the most famous, one of the most famous benchmark in high performance computing, stream benchmark, in order to test bandwidth on a single compute node. Here in the figure, you can see the bandwidth versus of number of OpenMP threads using for this test. In order to compare result of Fugaku supercomputer, I will always present result from Marconi. And here let's start from Marconi SKL orange line, where I was able to achieve maximum 203 gigabytes per second. On Marconi 100 partition, I was able to achieve already more, 236 gigabytes per second. However, on Fugaku, the result went extremely high, as I announced in introduction. We had 831 gigabytes per second of the main memory bandwidth. However, this result I didn't achieve automatically using default standard parameters on Fugaku supercomputer. And it's actually one of the main conclusions for this machine. Typically, you can achieve very high performance and high result of different benchmark, but this result needs to be tuned and adapted with different compilation and submission options. And for example, for this benchmark, using the standard recommended parameters on the web page of Fugaku supercomputer, I was able to achieve the same around value as Marconi 100 supercomputer. Afterwards, I contacted Fugaku support team and they recommended me to use different submission options and different compilation parameters. And with that parameter, I was able to achieve such high results. Now we came to the second benchmark. What I would like to show you today is the high performance Linpack benchmark, the one which is used to calculate system supercomputer performance for top 500 list. And I use this benchmark which solve a linear system of the dense matrix and convert afterwards the time of resolution time into the performance rate. I use this benchmark for a single node, and I achieved on Marconi supercomputer 2.17 teraflops, which is around 67% of theoretical peak performance. On Fugaku, I was able to achieve 1.87 teraflops, which is around 61% of the theoretical peak performance. I thought this value is a little bit low, and I contacted Fugaku support team, which was really helpful with all my tickets and all my questions, and answering time was a bit sometimes longer, takes a few days to several weeks, but they helped me with all my questions. And for example, here, they again recommended me use some different options. And it's always not the standard and regular parameters in order to improve my results. And with their additional help, I was able to achieve the peak performance of 2.15 teraflops, which is already 70% of the theoretical performance. However, if we compare this result with the result what Fugaku support team achieved to the test which used for top 500 list, and they got around 82% of the theoretical peak performance. I still don't know why we had such a difference. It's maybe that Fugaku support team for their test used a whole memory of complete node, and I had access only to 27 gigabytes. Now we came to the test of the internode. Fujitsu company also developed a special interconnect of Fugaku supercomputer. This interconnect named TOFU-D, and the specific of this interconnect lies that each compute node connected with its 6 neighbors. Schematic view you can see here in the figure. So one node represented here by a sphere has connection to its 6 neighbors in the horizontal, vertical, and tangential direction. Such a connection called TOFU network interfaces, and we have, as I said, 6 such interfaces. peak memory bandwidth of one side of such a connection is 6.8 gigabyte per second. So if we compare to Marconi, when we use peer-to-peer communication, only two compute nodes. On Marconi, we will have 2 times higher, 12.4 gigabyte per second. However, when we make our data transfer simultaneously in 6 directions, which can be the case in, for example, in 3-dimensional peak simulation, we will get theoretical bandwidth of 40.8 gigabytes per second. And it's again one of the conclusions from the Fugaku supercomputer. So in typical, we can get high result and high bandwidth, but we need to adapt our application in order to have such a bandwidth. So in order to test such a bandwidth, I use the benchmark, call it Intel MPI benchmark, and newly developed to test uni and bidirectional tests from this benchmark. Here in the figure, you can see the bandwidth, internode network bandwidth between 2 compute nodes versus different tested message sizes. So let's start line by line. For the unidirectional bandwidth test, I was able to achieve 6.2 gigabyte per second on Fugaku supercomputer, which is blue line represented in the figure. On Marconi, orange line, I was able to achieve 2 times higher, 12.1 gigabyte per second. But here I want to stress again that I tested only 2 nodes peer-to-peer using only one TOFU network interfaces. For bidirectional data transfer, I was able to achieve 2 times higher bandwidth for both Fugaku supercomputer, gray line, 12.1 gigabytes per second, and Marconi, 24.1 gigabyte per second, as we expected. So as you can see here, using only one TOFU network interfaces, result on Marconi are higher in comparison to Fugaku. However, when we use communication as it was announced and as Fugaku network was built in 6 directions simultaneously using 6 TOFU network interfaces, our bandwidth increased up to 38.1 gigabyte per second for unidirectional test, already a few times higher in comparison to Marconi. Now we came to the intranode test. Fujitsu company also specially developed for Fugaku supercomputer internode connection. As you remember from introduction, Fugaku compute node consists of 4 core memory groups, 4 sockets, and these sockets must be connected somehow between themselves. And Fujitsu company introduced so-called a ring intranode connection. Such ring connect 4 core memory groups, 4 sockets into one network. The theoretical unidirectional bandwidth of one of such ring is 128 gigabyte. In Fugaku supercomputer, 2 of such rings are introduced, showing here in the figure. So in total, we have 256 gigabyte per second of unidirectional bandwidth or 512 gigabyte per second of bidirectional bandwidth. I tested this network using the similar benchmark as before from Intel MPI benchmark suite and cross-check this result with also micro benchmark. Here you can see the similar figure as before, bandwidth versus the different tested message size, but for intranode network, what I call it also inter-socket bandwidth. And let's again start line by line. In Fugaku unidirectional bandwidth test, I was able to achieve from 2 different benchmarks around 230 gigabyte per second, which is around 90% of the theoretical bandwidth, which was really nice achievement. It's yellow and green lines. On Marconi, I was able to achieve only 75 gigabyte per second of unidirectional bandwidth. Surprisingly for us, when I did a bidirectional bandwidth test on Marconi, I was able only slightly increase our bandwidth to 81 gigabyte per second. I opened a ticket with Marconi support team and Intel support team, and they confirm my result, and this ticket is still under investigation. However, let's come back to Fugaku. And when I did bidirectional test on Fugaku, the bandwidth really increased a lot, as we expected, to 386 gigabyte per second, which is around 75% of the theoretical value. Now we came to the main part of this project, which was actually dedicated to test how easy it will be to transfer a real production code on Fugaku supercomputer and which performance we can get without really tuning of the code, but just manipulate it a bit with compilation and submission options. And first code which I transferred on Fugaku supercomputer was Onyx code, which is pure MPI code, three-dimensional particle in cell code, which doesn't use any external libraries. Here in the figure, you can see real-time execution of this code versus the run number. Red cycle represent result on Fugaku supercomputer, and blue triangle represent result on Marconi supercomputer. As you can see, result on Fugaku were really stable and a bit faster as on in comparison to the Marconi. I also did profiling of two codes for different supercomputer. And what I figure out, one of the main conclusions for this presentation, if our subroutine is memory bound, the results were faster on Fugaku. If our code is compute bound, the results were faster, subroutine were faster on Marconi. And this result could a bit mislead the users because they were not done for the real production test case. They were done for special test case I developed for the Fugaku supercomputer because this code used really a lot of memory. For the simulation, it's used a lot of macro particle which doesn't fit to the memory available on Fugaku supercomputer. As you remember, it is only 27 gigabyte. So I, by purpose, reduce amount of the simulated macro particle to the case which fits to Fugaku supercomputer. Therefore, subroutines, which is typically compute bound, like a particle pusher or charge projection into the P grid, now doesn't take so much time as it would take in the real production case due to the number of real macro particles. Therefore, for the real production case, we will have the similar result between Fugaku and Marconi, or even Fugaku will be a bit slower. The second code which I transferred on Fugaku supercomputer was the Starwell code, and it is as well pure MPI code which use only one external library, ScalaPack library. Here in the figure you can see the similar result as before, work clock time versus the run number. However, now Fugaku is much slower in comparison to the Marconi. And I did again profiling of these two codes, and I found really similar result. When the code is compute bound, we are much faster on Marconi. And we know the Starwell code, the kernel loop of the Starwell code is really compute bound. This code in original version used very large temporal matrices, which didn't allow us to scale the code for very large run. Therefore, the algorithm was changed, and these very large matrices were replaced by a computation, what we call it matrix-free calculation. And these computations are very heavy. Therefore, Starwell code is complete compute bound, and it's actually why again it's slower on Fugaku in comparison to Marconi. And here is the main conclusion which I would like to repeat again. If your code is memory bound, the code could be faster on Fugaku without any adaptation. If the code is compute bound, direct transferring on Fugaku supercomputer makes this code slower on Fugaku in comparison to Marconi. However, I am quite sure that if we look inside the code and change somehow algorithm and calculation, we could improve significantly result on Fugaku. We also tried to port two other code named Urtopi and Gene on Fugaku supercomputer. However, these two codes use already quite significant number of subroutines of different libraries like NCDF, HD5, and PETC, which were not in the beginning available on Fugaku supercomputer. I asked support team to install the necessary library, and they, as I said, were very helpful and tried to install it finally all of them. However, installation period was between 1 week and several weeks, or even to 1 month. And it was not in time till our project finished 31st of March. So we were not able to use all this library and test our codes. This is all what I would like to present you today. And I would like to thank you for your attention, and we'll be happy to answer on your questions.
Thank you very much, Siri, for the talk. Is there any? Yeah, I see Thomas. Please, can you unmute?
Good morning, Sergey.
Hello.
I have two questions if there's time. My first question is, when you were talking about the total network, and you were talking about these 6 links per node. My question is, can these 6 links be saturated from a single core group, or what you were calling a socket, or in order to fill to saturate these 6 connections, which is 60 gigabytes per second, do these need to be coming from 2 different groups of cores?
So I didn't test it, Thomas, this, but I expect that we can saturate it, because if you take a look on the internet connection, in order to send data from one compute memory group, from one socket to another one, we use different networks, this intranode network, and the peak memory bandwidth is 128 gigabyte, and we were able to achieve on our next slide. Well, it's only one ring. With 2 rings, we get 256 gigabytes, and these 2 rings can be used with 1 core memory group. And I achieved around 230 gigabytes. So we can assume that this is not a bottleneck, and we can transfer our data from one socket to another one with very high bandwidth. And afterwards, when we use internet connection, we can use already data from another socket without any bottleneck.
Okay.
So short answer on your question, I think yes, we can saturate it with 1 socket with 1 core memory group.
And my second question is on slide 11 for the Onyx example.
Yes.
The final profile subroutine, the add particle, this is by far the strangest to me of the data.
I know, it was also very strange for me as well. And I didn't know, I didn't test it. I didn't have enough time to test it. But even if something like strange happens there, the main conclusion still persists for all other subroutines like particle pusher, Poisson solver, charge projections. They are consistent. This one could be, well, we should take a look what happens there.
Okay, thanks.
Okay, any other question for Siri? Okay, I assume no. Thank you very much, Siri, for the work you share. I think it's really important for many of us who are interested in working on Fugaku and A64FX. So let's move to the next talk. So the next talk is given from Mei Yamasan, and Siri, I need you to click on Mei Yamasan to make him host, please.
couldn't find.
So it's you need to go on the participant list.
Ayama-san.
So Franz, I think I did.
Okay, you gave.
host,
Yeah, no problem. No problem. You did it right. Okay, so my Yama-san, normally it's
okay.
working now.
Thank you. Let's see. Okay, can you see my screen?
Yes, absolutely.
Okay, so thank you. My name is Shinya Mayama from Nagoya University. Yeah, today I would like to talk about gyrokinetic simulation of our multi-scale turbulence simulation on the supercomputer Fugaku. This work is partially supported by MEX as program for promoting researches on the supercomputer Fugaku. And the project name is Exploration of Burning Plasma Confinement Physics. Okay, this is the outline of my talk. The first part is a computational part. I would like to talk about optimization of GKB code on the supercomputer Fugaku. And the second part is more physical results. Okay, so the GKB code is the plasma turbulence simulation code based on delta F gyrokinetic equations. So it is a 5-dimensional Eulerian solver. We resolve 5-dimensional phase space, x, y, z are configuration space, and v parallel and mu are the velocity space. It is parallelized by MPI and OpenMP, and the simulation is solved in local flux tube geometry like this. So we can employ quite high resolution in this thin local flux tube, so we can resolve multi-scale simulation from ion to electron scales. The code is now available online, so you can freely download from our homepage or GitHub repository. GKB code was originally developed by Watanabe sensei around 2005 or so. At first, it was applied for the ion scale simulation in simple tokamak plasmas, and electron model was adiabatic. But after that, it was applied more complex LHD plasma or multi-scale turbulence using the K computer around 2012 here. And now it is running on the Fugaku. It is applied for the analysis of multi-scale turbulence toward burning plasmas, employing electron, deuterium, tritium, and helium mixtures. So the physics model of GKB is extended along with the development of HPC. Okay, yeah, actually, almost everything was introduced in previous talk, but in this slide, I would like to give brief explanation about Fugaku architecture. It has 158,000 nodes. It is connected by 6-dimensional TOFU interconnect. It is a 3-dimensional torus network from a user view, and each node contains one CPU, A64FX, developed by Fujitsu. And it is, as explained, it is a new node. It contains 4 core memory groups, and each core memory group contains 12 computation cores. So multiplying 32 flops and 2.2 gigahertz and 12 cores and 4 core memory groups and 158 nodes, then we get theoretical peak performance 500 petaflops. Actually, GKB code has already been quite optimized for the previous Japanese flagship supercomputer K computer. So this figure summarizes difference from K to Fugaku. Of course, right column is the same parameter presented in the previous talk. So by comparing K and Fugaku, surely the computational performance per node is enhanced, and fortunately, memory bandwidth is also quite enhanced. So memory bandwidth per flops, this is an important parameter of the code which is limited by memory bandwidth. But this factor is still high. On the K computer, it was 0.5, and on the Fugaku computer, it is 0.3. So this high memory bandwidth per flops allow us to utilize memory bandwidth limited code like CFD application, like including GKB code. On the other hand, interconnect bandwidth is just small increment. So it is just twice from K computer. So memory, interconnect bandwidth per flops is significantly reduced. This is just 1/10 or so. So from the application, this computation cost ratio becomes much severe. So we need to increase arithmetic intensity to utilize this high performance on the Fugaku architecture. In this slide, I would like to explain typical computation and communication in the GKB code. It solves gyrokinetic Grasov equation and Poisson and Ampere equation. So we employ 5-dimensional phase space, as I said, x, y, z, and v parallel and mu direction. And we also treat various plasma species. So this S means the species. This 6-dimensional array is decomposed by MPI. In this case, y, z, v, and mu and s direction are decomposed. Then to calculate, for example, this Poisson and Ampere equations, we need to evaluate current and densities. So we need to apply MPI or reduce among velocity space and particle species. But this cost is not so expensive. The other communication is the point-to-point communication to calculate finite difference in z and v parallel direction. These are parallel field-aligned coordinate is the z direction, and v parallel advection is also calculated. GKB code also contains two types of MPI all-to-all. First one is applied for the calculation of spectral calculation in perpendicular x and y directions. So we need to calculate parallel to the FFT. For this implementation, we make some improvements. So I will explain this in next slide. And the last communication is the calculation of collision. Here we use implicit collision solver with using MPI all-to-all. I will also explain this later. Okay, so about the improved implementation of parallel spectral calculation, here I would like to compare as-is implementation and the new implementations. Here we would like to calculate a nonlinear advection term in x and y directions. It is in as-is implementation. Here I call it y2x transpose method. Then we decompose y direction initially, so we can apply Fourier transform in x directions. After that, we analyze, we apply a data transpose so as to change the decomposed axis from y to x here. Then we can now apply Fourier transform in y direction. Then nonlinear advection term is calculated in real space and it is transformed back to web number space. On the other hand, in the new y2zm transpose implementation, here initially a y direction is decomposed by MPI, but just before applying Fourier transform, we transpose this MPI processes which was used to decompose in y direction. It is now applied to decompose a combination of z and mu direction here, PW here. Then we have x and y direction globally. Then we can apply to the FFT and calculate nonlinear advection term, and it can be transposed back again. So comparing these two implementations, actually data transpose is reduced. In the as-is implementation, we need to transpose to calculate dx and dfdy component, and finally this nonlinear term is also transposed back. So three variables are transposed. But in this new implementation, here we transpose F directly, and dfdx is calculated by using this global array. So we need to transpose only 2 variables. And additionally, with considering 3/2 de-aliasing rule, the transposed data size is also reduced. Thanks to these reduced transpose communications, some tests in JFRS1 shows the calculation of nonlinear term is accelerated by a factor of 1.8. Another optimization is implicit collision solver. When considering Coulomb collision, velocity-dependent collision frequency severely restricts time step size. Because collision is just an integral differential operator over velocity space and particle species, so we first transpose so as to have v and mu and s direction to have globally. Then we apply to calculate iterative implicit collision solver for this global v mu s array. They are independent to z, y, x directions. So this iteration is indeed MPI communication free during iteration. After solving the implicit collision solver, it is transformed back again by using MPI all-to-all. So this is a short summary, but let's see only this table. This is the result on FX100, and this is the previous architecture under Fugaku. But from the compared with explicit implementation and implicit collision implementation, GKB code, its floating point operation is enhanced because iterative solver is implemented as MPI free, communication free during iteration. And implicit collision solver allows stable calculation even when we take larger time step size than the explicit restriction. So finally, we achieved that speed up to time to speed up to solution. It is 10 times faster. Each time step size, each time step, it takes twice larger as number of seconds, but its time step is much large. So totally, time to solution is quite reduced. So this implicit collision solver enhance arithmetic intensity and also reduce time to solution. So this is quite promising feature for many core processor like Fugaku computer. And I also applied another optimization technique. First one is the optimized process mapping of our 5-dimensional problem on 3D torus network. And the other one is the computation communication overlap by using MPI. Actually, these two techniques have already been developed in the K computer. And fortunately, Fugaku and K has similar TOF interconnect architecture, and OpenMP is surely OpenMP computation communication overlap is just a general procedure. So these two optimization techniques are available on Fugaku as well as K computer. Okay, so this is the weak scaling of GKB measured on Fugaku. This shows the excellent scaling up to our target problem size, 10 to the power 12 number of grids. Here we employ 12,000 nodes and achieved 3.1 petaflops. This is the 7.5% to theoretical peak performance, and its parallel efficiency is 83.7%. So it is reasonably efficient as a CFD applications. Bottom figure shows the breakdown of the elapsed time for each calculations. Actually, this blue line shows the elapsed time for collision. This thick one shows the computation part, and this colors shows the communication cost. As number of nodes increase, communication cost surely increases, but total elapsed time is not so changed because we successfully overlap computation and communication. So such a iterative computation efficiently masks the net communication cost. So collision term is almost unchanged, but unfortunately, yeah, this green one is the nonlinear term calculation, and red one is the linear term calculations. This communication cost increases as number of nodes increases, but it cannot completely be masked by overlap technique. So in this scan, elapsed time slowly increases. The last line is the also employed 12,000 nodes, but we did not use rank mapping in this case. We can see that if we do not use MPI process mapping, all-to-all for nonlinear calculation is significantly enhanced. So such a process mapping is quite efficient for large-scale calculation. Actually, in my experiments, if number of nodes is larger than 1,000 or so, such a mapping is quite effective. Okay, so shall we move to physical results? Here, recent gyrokinetic simulation reveals the importance of multi-scale interaction. This is our simulation, one of our simulations. We analyze cross-scale interaction between ion scale fluctuation and small electron scale fluctuation. Actually, such a small electron scale can affect on turbulent transport. Some experimental comparison also suggests that multi-scale interaction can be necessary to explain an experimental heat flux, or it can also be important in eta parameters. These two are reports from US, but there are some recent researches about multi-scale interaction from Europe. Our physical target on Fugaku supercomputer is extrapolation of importance of multi-scale interaction toward burning plasmas. So we would like to analyze such a cross-scale interaction by employing high electron temperature, because in burning plasma, a fusion-bound alpha particle mainly hits electrons. And we would like to also treat electron and fuel deuterium, tritium, and helium ash mixture plasmas. This is the result. Here in our employed parameter, small scale ETG and large scale trapped electron mode are destabilized. In this plot, we see that initially ETG modes rapidly grow up and saturate, creates high wave number components. But after that, trapped electron modes slowly grow up and saturate, and it becomes dominate. This is orange line. And this blue line also, this plots the low resolution ion scale simulation treating only trapped electron modes for comparisons. So from this figure, we see that in the presence of ETG turbulence, TEM growth rate is reduced and its saturation level is also reduced compared with ion scale simulation. So this suggests that ETG, small scale ETG, can stabilize ITG, large scale TEM. And this also suggests the importance of multi-scale interaction even in burning plasma parameters. This is a color map of perturbed electron pressure. Here is hot electron pressure perturbation, and here is the cold ones, and so on. And this black lines is a streamline of turbulent E-cross-B flow. So this means, cause in large scale trapped electron mode, high electron temperature region is go outward and a low electron temperature region goes inward. So there is a net transport. This is a typical feature of trapped electron mode. But in this magnified picture, you can see that small scale ETG fluctuation coexist with large scale trapped electron mode flows. So this suggests that such a small scale ETG turbulence can disturb and dissipatively stabilize such large scale TEM flow structures. Actually, such a cross-scale interaction have significant impact on turbulent transport. right figure shows the spectrum of electron energy flux. This orange dot is the plot about the initial ETG saturation in multi-scale simulation. Here is the peak of ETG, and this green dot shows the final saturated state. Here is the peak of TEM, and here is also peak of ETG. But in this plot, we can see that in the presence of TEM, ETG peak is significantly reduced. And by comparing multi-scale simulation result and ion scale simulation results, these blue dots, we see that TEM peak is also reduced in the presence of ETG. Actually, this suppression, this reduction significantly suppresses the heat flux. For the electron heat flux, we observe QE equal 500 in the gyro bomb unit in ion scale trapped electron mode simulations, but in multi-scale simulation it is reduced to 88. So this results firstly demonstrates the possibility of reduction of total electron heat flux by cross-scale interactions. And surely it affects not only on electron, but also pure deuterium, tritium, and helium ash transport. All of them are affected. Here, this plot I would like to show there is a significant contribution from trapped electron particles, but let's skip this slide. So this is a schematic explanation of TEM-ETG cross-scale interactions. As well known, trapped electron mode is destabilized by the resonance of TEM waves and trapped electron particle precession drift in toroidal directions. Right figure is such a particle trajectory calculation. This y direction is the toroidal precession, say toroidal angle or something, and this is the electric field called radial equals v drift, and this right figure is the radial displacement. If particle is non-resonant case, the particle moves like this blue lines. So particle fields waves, but it oscillates just in positive x and negative x direction. It cancels out. But if it is resonate, if particle trajectory resonates the wave, it always feels the equals v in the same direction. So it is transposed in this case outward here, like black line. This is the trajectory calculated by TEM oscillations. But if we include ETG fluctuations, the particle fields, not only TEM electric field, but also here is a strong spike caused by small scale ETG. So it disturbs the trapped particle electron trajectories. So it may reduce the precession drift resonance between TEM and trapped electron. This is the mechanism of stabilization of TEM in the presence of small scale ETG turbulence. The other interaction is the interaction from large to small scales, where trapped electron turbulence causes large eddy shearing. So its shearing tends to stabilize ETG streamers. Now, this is somewhat in contrast from previous results reported by our co-workers. He stressed that it's the importance of the appearance of zonal flow by TEM turbulence, but even when no strong zonal flow, such as TEM turbulent eddy, effectively shears the ETG streamers. This is our analysis. Okay, so this is the summary of my talk. From the high performance computing, GKB capability is extended along with HPC. So Fugaku architecture is quite efficient because high memory bandwidth, but interconnect bandwidth is not so it is still small. So we need to reduce communication cost by using mapping or overlapping or some improved implementation techniques. We finally achieved excellent long excellent scaling around 3.1 petaflops. Then the highly optimized codes applied to the analysis of multiscale turbulence toward burning plasma. Here, we see that such a cross-scale interaction may change the turbulent transport spectrum and affect on turbulent transport, not only electron but also fuel deuterium, tritium, and helium ash. The results firstly demonstrated the possibility of reduction of electron total heat flux by cross-scale interactions. We have also analyzed physical mechanism of large to small or small to large scale interactions. So from our experiments, we see that in this case, TEM stabilized ETG and ETG also stabilized TEM. So these two seems to be mutually exclusive. Actually, such mutual exclusive nature is often observed. Similarly, ITG tends to stabilize ETG or ETG tends to stabilize MTM. So this could be a general feature, mutual exclusiveness between disparate scale turbulence. This is the end of my presentation. Thank you for your attention.
Thank you very much, Mayama-san. So do we have any questions for Mayama-san? If so, please unmute yourself. Okay, Thomas, please go ahead.
You showed a very nice figure with the transpose and the FFTs, where you had this improvement due to the overlapping, essentially, if I understand, on the previous, on slide 11.
This one?
So this one on the right-hand side with the overlap. My question is, to what degree do you need to try to do this yourself with the FFT in X, the transpose and the FFT in Y, or were you able to find a pre-existing library which does the FFT and the transpose for you, or was this all manual?
Actually, I've not compared such an existing parallel FFT, but this is just an example. Actually, I apply the similar procedure not only parallel FFT, but also, for example, calculation of collision term. In this case, I pipelined in the direction. So data transpose and iterative solver are overlapped by pipeline in this direction. Similarly, this MPI point-to-point communication in ZV direction is also pipelined in mu direction. So finite difference and point-to-point communication is again overlapped. So this methodology itself is quite general. So I've utilized such a procedure in all calculations in GKB. It is quite efficient and general.
And is it difficult in order to write and to maintain this, or is this easy?
At least for me, it's easy because it's only depend on OpenMP. This is quite simple implementation. Just after pipelining using master directive, master thread only treats the transport communications, and the other thread can calculate independent calculations simultaneously. So it is quite a general implementation in OpenMP. And the additional advantage there is because if we transpose, for example, in this case, one may require 5-dimensional temporary array to make data transpose, because we may apply FFT in X direction, whole directions. So you may prepare 5-dimensional array, then it could be transposed. But in this pipeline procedure, it is somewhat decomposed in, say, mu direction or so. So each transpose is only done in 4D. So temporary memory size is also reduced. So actually, as in previous presentation, memory size on Fugaku is quite small. So we need to elaborate. We need to make effort to reduce such a memory size. So this pipelining is efficient for computation communication overlap and reducing memory sizes.
This is very nice. Thank you.
Thank you.
Thank you. Do we have any other question for Mayama-san? Okay. Mayama-san, would you mind giving me back the hosting right, please?
Okay, thank you. Let me see.
Thank you very much.
You are now host.
Thanks. Okay, so the next point in the agenda today is the virtual group photo. So if you don't mind, could you please turn on your camera, please? And I will take care of the group photo. Okay, so that's in 2 shots. Okay. So the first group is taken. Give me a few seconds. Stay on. Okay, there we go. And a few more seconds. Thank you, Dirol. Thank you very much. You can turn off your camera. I think I have almost all of you. Okay, so the next point in the agenda is a talk from Alessandro Biancalani. So Alessandro, I will give you the right to share your screen. And
hi, good morning, France. Yes.
Here we go. So now you should be able to share your screen.
Okay.
Okay, so we see your screen. Yes. It's not in present. Okay, it's in presentation mode.
It's fine. Okay.
Yep.
So can you see it fine? Everything is.
Yes, yes, absolutely. We see the presentation mode perfectly.
Okay, so let me start. Thanks, first of all, for giving me the opportunity to give this talk. And the topic of this talk is the nonlinear dynamics of zonal structures with OR5 in the framework of the ORB zone numerical project in Marconi and M100. This work has been carried out with the help of several people, and I've listed here my main collaborators. The full list of the collaborators is found in these 2 papers, which are the papers where I took the material from. And let me also mention 3 Eurofusion projects, which are the main 3 Eurofusion projects where I've taken this material from. So this is the outline. I'm gonna show the introduction and motivation, the talk about the model. Then I'm selecting 2 physical production cases because this talk is from the point of view of the user. And so what I took is 2 actual production cases, which I published in 2 papers, which are the papers that I showed in the first slide. And for these 2 cases, I'm going to describe the case and then I'll show the efficiency in M100 and finally the conclusions. So let's start with the introduction motivation. The reason why we're interested in turbulence in tokamak plasmas is that we have radial temperature and density gradients, and these drive micro instabilities. The nonlinear coupling leads to turbulent states, and these turbulent states are often observed in the presence of zonal flows. By zonal, I mean axisymmetric flows. Turbulence carries heat fluxes, modifying the equilibrium temperature profile. So this is bad for confinement. We want to have some modeling of this. The turbulence in tokamak core is relatively well understood because in the last decades, gyrokinetic simulations have made a remarkable progress, including the addition of collisions, impurities, electromagnetic effects, global effects, etc. On the other hand, the edge is still challenging. The Jarkey model typically used in the past was either studying the turbulence alone or global instabilities alone. By global instability, I'm talking about, for example, MHD instabilities. And the reason was mainly technological limits. When I say global instabilities in this talk, I will refer to energetic particle instabilities. And energetic particles in the mega electron volt range are present in ignited plasmas, either because of fusion, they are fusion products, or because they are produced by auxiliary heating, like current drive or current drive systems. These energetic particles can exchange energy with the plasma oscillations via inverse Landau damping. So plasma oscillations can become unstable. One of the type of instabilities that I'm considering here is alpha modes. These are transverse global electromagnetic perturbations which are excited by energetic particles. Another type of instability is the energetic particle-driven geodesic acoustic modes, and these are electrostatic oscillating zonal flows. An example in a ASDEX subgrade shot of measurement of these different kinds of modes is here on the plot here, and you can see there this is the induced alpha eigenmodes, reverse shear alpha eigenmodes, and EGAMs as well in a Mirnov coil measurement. The ultimate goal of our numerical approach is the self-consistent simulation of global modes like alpha modes and zonal flows, and turbulence and energetic particles. Let me mention something about the model. First of all, why do we need a kinetic model? A kinetic treatment is known to be necessary due to three main reasons. The first is that when we are at low frequencies of the order of the transit ions, then the resonances with bulk ions substantially modify the MHD predictions. The wave-particle interaction is the main responsible for the energetic particle drive, so it's obvious that we need to keep it into account with a kinetic model, and the energetic particle transport therefore can be predicted only with a kinetic model for the energetic particles. The kinetic modifications are important to the wave-wave interaction, especially when we go to K per rho I of the order 1. The frequency of the modes that we are considering is much lower than the ion cyclotron frequency. Therefore, the fast ion gyro motion around the magnetic field lines can be averaged out. We go from 6D to 5D in phase space, and so we get to what the model which is called gyrokinetics. The numerical simulations are numerically demanding in comparison to a fluid model or a hybrid fluid kinetic model. Therefore, we need a smart numerical scheme and a parallelization to simulate experimental configurations. The gyrokinetic code we are talking about here is OR5. This is global gyrokinetic particle in cell electromagnetic code. More details can be found in the recent paper of Emmanuel Lant in 2019. Let me just mention here that it's a particle in cell code, therefore we have the trajectories to push the markers for each piece. We have a gyrokinetic Poisson equation for the time evolution of the scalar potential, and the Ampere equation for the time evolution of the vector potential. Electromagnetic particle in cell simulations are known to be affected by cancellation problem, but this has been strongly mitigated recently via the controlled variate scheme, and then more recently with a pullback scheme, which was described for the implementation of OR5 in this paper by Alexei Mishenko in 2019. OR5 has been enabled for GPUs in 2019, and the details can be found in this paper by Noé Ohana in 2000, which appeared only this year in 2021. And other GPU-enabled gyrokinetic codes include GENE, GTC, CGyro, and XGC. And the code was then ported to M100 after some tests on PIDSDANE and Submit, and it's now ported to Marconi 100 with the work done by Thomas Hewa-Schneider. Originally, this was pure MPI based on domain decomposition, efficient in toroidal direction in axisymmetric geometries, and domain cloning, and now uses a hybrid MPI OpenMP and MPI OpenACC. So the computations involving the markers are now offloaded to the GPUs. You can see here a typical cycle, a typical loop of the gyrokinetic particle in cell code. So all these operations except the solve, which is done on the fields, are now offloaded to the GPUs. The communication between the GPUs and CPU is minimized by keeping marker data on the GPU only. Let me mention, before going to physical production cases, let me mention one strong scaling which was obtained with an electromagnetic simulation on Summit. And this is the result. Each of these lines is a strong scaling case, and you can see for different concentrations the different scalings. So we had a very nice strong scaling here, as you can see, and more details can be found in the paper of Noé Ohana in CPC in 2021. So let me start by describing the first problem that I've selected. This is the energetic particle distribution by EGAMS. So the main physics of EGAMS is the one of the inverse Landau damping. So what we did in these papers was to try to do a comparison between the EGAM, which is an instabilities in 3D geometry of a tokamak, and a 1D problem, which is the beam plasma instability in electrostatic one dimension. So Langmuir waves, which are the basics of these beam plasma instabilities, are longitudinal perturbation of the electron pressure. The characteristic frequency is the plasma frequency, and they are affected by Landau damping. So here you can see the distribution function. In this case, it's the distribution function of the electrons. If we have a region with a positive gradient of the distribution function in velocity space, then this Landau damping becomes an inverse Landau damping. So this plasma wave, which is the Langmuir wave, becomes unstable and becomes a beam plasma instability. Due to the nonlinear wave-particle interaction, the passive electrons can lose energy. They become trapped in the potential wave created by the electric field of this wave, and they stop exchanging energy with the mode. And this is one of the main reasons of saturation of this instability. So let's now go to see the EGAMS. EGAMS have been studied extensively in the past by analytical theory, numerical simulation, and experiments. And if we want to do a comparison with the beam plasma system, the first thing we see is that in literature there was already a relation which was linking the bounce frequency of the particles in the electric field created by the EGAMS with the electric field itself. This is the relation that we get with the coefficient of proportionality, which was calculated analytically in this paper by Jion Cho in 2011. What we did with R5 was to close this relation by adding another scaling, which is the scaling of the radial electric field with the linear growth rate of the EGAMS. And so what we obtain by putting together these two relations is the proportionality relation between the bounce frequency of the particles, of the energetic particles in this case, and the linear growth rate of the modes. Beta is a coefficient of proportionality which depends on the energetic particles concentration. We can normalize it to the sound frequency, and then we can see that there is an omega inside, which is proportionality, which is depending on the energetic particle concentration, but this can be taken out with this normalization. So we get a beta zero, which is a coefficient which is characterizing this instability, the EGAM, and which is not depending on the energetic particle concentration. Let's see some scaling when we put in practice these analytical relationships or quasi-analytical relationship, because alpha is taken from simulation. So the quadratic scaling of the saturated electric field can be seen here. This is the radial electric field versus the linear growth rate. Note that for different plasma temperature, we have different scalings here, as you can see. But when we go to see the dependence of beta on the linear frequency, you can see that all the dots, these points go together in the same scaling. And when we go to the limit of omega linear going to the GAM frequency, namely the concentration of fast particle going to zero, we get to one single point, which is the beta zero value, which I was mentioning. We measure 2.66 for the EGAM, and let me also report here the value of the beam plasma stability, which was slightly higher. We're now studying the possibility of this being depending on the localization of the energetic particle distribution function. So this is just to show what we can do with simulation, which are not turbulent simulation. These are many, as you can see, many simple EGAM simulation with only one toroidal mode number. And we can study the scalings of these general rules, and we can compare with analytical theory with the simulation. Let's see what happens when we go from CPU to GPUs. First of all, let me mention that one typical EGAM simulation is a convergence with 256, 32, and 4 points in the spatial directions. This is the time step, the number of markers in total, which in this case is only thermal ions and fast ions. We get 244 markers per cell. The nonlinear saturation is achieved in 1,500 time steps. So let's now compare in Marconi. We got one simulation of this was running in 28 minutes in 4 nodes. And in M100, we get now one simulation running in 7 minutes. So we get a factor of 4 of gain. And we can also see that 4 is a good compromise when we do a strong scaling, as you can see here, when we take exactly the same input file and we just running with different nodes. So let me also mention that OR5 weak scales with respect to the markers. Okay, so let's go to another problem, which is a completely different simulation. We have here a global simulation with turbulence, alpha modes, and zone abstraction and energetic particles. This was studied because now we are now interested in what happens when the energetic particles are added to a turbulent simulations. It's a problem of very strong interest in the recent years. There are a lot of simulations, analytical theory, and experiments with this problem as well. In this simulation that we ran, we had initialized the noise at t equals 0. We have 3 species where the third species is the energetic particle species, but we have this energetic particle species set with temperature equal to the thermal ion species in the first part of the simulation. So it's just a minority which is not really energetic in the first part of the simulation. This is just to have a turbulent simulations up to a certain point. You can see the non-zonal component of the radioelectric field and the zonal component of the radioelectric field here. Then we switch on the energetic particles by increasing the temperature of the energetic particles. We also modify the gradient, by the way, of the density of the energetic particles here, but here this has no effect alone. We have cross-checked this. We included several toroidal mode numbers here, as you can see, and we have sources in the form of a Crook operator conserving the zonal fields. These are applied only to the thermal species, and they restore the thermal profiles. We have now the coexistence of alpha eigenmodes. In this case, these are Beer-induced alpha eigenmodes. You can see here macroscopic instability, which is a Beer-induced alpha eigenmodes in the bottom right panel, which is just after switching on the energetic particles. Before switching on the energetic particles, this is a turbulence, typical turbulence simulation. This BAE saturates due to the energetic particle redistribution. In this case, the BAE electric field is higher than the ITG for this energetic particle concentration, which was 1%. The zonal flows are also observed to be very strong. In this measurement here of the simulation, you can see that the zonal flow excited by turbulence has a certain amplitude, but when we switch on the energetic particles here, for only 1% of energetic particles, as I said, the zonal flow can go to very strong levels, as you can see here. And this also shows us that there is a role of zonal straws which strongly depends on the localization. As you can see, it has different radial positions. So it's an intrinsically global problem because you need to see where the turbulence is, where the alpha modes is, and where the zonal flows are to understand how the interaction will occur. Similar simulations, but with the local model, have been also published recently in nuclear fusion by Alessandro Di Siena. Now, let's see what happens when we go from Marconi to M100 for this particular case. Let me mention that one typical simulation for this case has a resolution of 128, 192, and 96 points in the space direction. This is the time step. The toroidal, the number of markers is this one. So we have 74 markers per cell for this resolution that we have shown here. The saturation of all modes, namely turbulence and alpha modes, occurs in 26,000 time steps. This is what we need for one whole simulation. So this simulation runs in 3 days in 12 nodes, and we had it in 12 days in 10 nodes in Marconi. So we have still a factor of 4. We can also increase the resolution and the number of markers, as you can see in this panel here. The blue line is given by the points with this nominal resolution, and the green line, which you can see here, is the other points with the double resolution in each direction and a factor 8 more of number of markers. I also report for visualization here the same speed, but multiplied by a factor 8, which is which are the red points here. So OrbZone in M100 allows to have simulations which are run now in a reasonable time, and we can study this complex multi-scale system. For high resolution simulations were done with both the OrbZone project, which is what I'm using for most of the results shown in my talk today, and also with PRAISE, with Alexei Mishenko as the principal investigator. So let me go to the conclusions. We have a gyrokinetic particle inside code OR5, which was enabled for GPUs in 2019 and ported to M100. Two physics production cases have been chosen here to study the efficiency in Marconi and M100. The first case was a single toroidal mode, n equals 0. This was an EGAM. The study of many simulations with different equilibria had the formulation of a reduced model obtaining a simple analytical formula for the prediction of the saturation amplitudes. Simulations in M100 are 4 times faster than in Marconi. Alphen modes, zonal flows and turbulence with broad spectrum of toroidal modes are also taken into example for the case B, and one single simulation needs many markers for studying the excitation of zonal flows by Alphen modes and by saturated turbulence. Simulation M100 are 3 to 4 times, let me say, faster than in Marconi, which helps a lot for such long simulations. And for optimal resolution, we also needed PRAISE, so we had a collaboration between OrbZone and PRAISE. So this is all for me, and let me just put the acknowledgements slide, and thank you for your attention.
Thank you very much, Benkarani-san. So do we have a question, Alessandro? Okay, so I assume it's no question. Thank you again, Alessandro.
Thank you.
Could you please give me back the hosting right? You just sorry, you need to click on my name in the participant list, and that should be something like this name as a host.
Yeah, make host.
Mm-hmm. Thank you very much.
You're welcome.
Okay, so let's move to the next talk, and the next talk is from Masatoshi-san. So Masatoshi-san, I will give you the right to share your screen. Just give me a second. I don't see you in the list, Masatoshi-san.
Masatoshi Yagi.
Okay, so give me a second. Yeah, there you are. So now you should be able to share your screen, Masatoshi-san.
Okay.
Okay. Okay, we can see your screen.
Okay, so my name is Masatoshi Yagi, and today I'll talk about the benchmark test 12 GPU implementation of Tyrant's code. And we acknowledge NVIDIA Japan for GPU implementation of GKNet. So my talk is 2 parts. One is benchmark test of global gyrokinetic code GKNet on GPU. So first part is done by NVIDIA Japan, And second part is a benchmark test for should spectral code R5F on GPUs. Okay, so the first part, testing environment and conditions as follows. So we use a machine, DGX station. This machine consists of CPU, Xeon CPU E5, and GPU V100, 4 GPUs. And the operating system is Ubuntu. And compiler, we use NVIDIA HPC SDK 21.2 and OpenMPI. And in this code, we use P3D FFT and FFTW. And this is typical parameters for this benchmark test. Here, NX, NY, NZ, and NV and NU, these are the mesh number, each three real space and velocity space. And this result is a single CPU runs. So we use one node and 16 processes used. And and here this figure shows the time history. So you can see like a gyro or a newt or something. So, and single iteration time is 3.98 seconds. And the gyro part is 2.89 seconds, roughly 73%. And the neutral part is 0.67 seconds. So this gyro part is a very heavy, very costly parts in this code. Then we use 4 GPU runs. So these 4 GPUs and 16 processes. And in this case, you can see single iteration time is 320 milliseconds. And gyro part is 167 milliseconds, roughly 52%. And neutral part is 122 milliseconds and 47%. So if we compare these two previous case and this case, almost 10 times faster if we use a GPU in this the gyro and the neutral parts. And actually, this code consists of these subroutines. So the gyro.f90 and include the neutral and the gyro case. And also we have output F90. This is output subroutines, and FLR and LU and FFT and so on. And in this figure, green color shows a GPU and the calculation almost done in GPU. And thin green color, it means neutral and main parts. These are partially on GPU. Other part like P3D FFT or LU, these are done on CPU. And this is the modification of each source code. So we have this hotline source, and this green and mark means the modification source code. And the heavy part is gyro.f90. This part is heavy part. And in this program, especially this gyro part, to overlap calculations and communication in gyro, shape of arrays, namely moment local and moment total, changes as. This is 1, 2, 3, 4-dimensional arrays, and we change it to the orders like the first argument is just come to the last argument. And the calculations as a communication of these arrays separated into three pieces. So this is just an example of the source code. And you can see this moment local, these arrays. This is just, we have three loops, like last argument is 0 case, I show here. And so the overlap between the communications to CPU and GPU and calculations like this. So this kernel part is asynchronized, and this is loop vectorizations and update self. So we just send data to GPU to CPU in this command. And so similar, the iteration and the appear to last argument 1 and 2. And the other part is bounded for F. To use GPU direct, MPI subarrays change to standard implementations. Originally, we use MPI subarray. And this is 3 steps, like packing of data into communication buffer, and MPI I send, I receive, perform using communication buffer, and unpacking of data from communication buffers. So this is just some example. And you can see if we use the GDR, we use the host data use device, and the other case, without GDR, just write update self. Okay. And now this, the code also just implement on Marconi 100. And so this machine consists of IBM Power 9 and the GPU NVIDIA V100. So this parts, GPU part is the same to GDX machines. And on Marconi, we use CUDA and HPC SDK. And but the difference between the GDX and Marconi is memory, because original GDX have 32 gigabyte memories on each GPU. However, in Marconi, only 16 gigabytes. So we need to change parameters to reduce the memories. So in this benchmark, we changed to NX is 64 instead of 96, and NV is 32. And so this is a comparison between only CPU simulations and using GPU simulations. And this browser part, this corresponds to gyro part, actually. And so the on Marconi case, we can see like more than the 40, sorry. Five times, the faster than the CPU case. And so this red, the color show the GPU case is faster than CPU case. However, other part like a green show these parts, it becomes worse. And essentially, these, the send receive or neutral case. This is P3D FFT. This is on CPU case, and LU decomposition use this matrix cases. And the send receive use MPI I send iris. So communication parts and some calculation on CPU parts becomes worse. And finally, if we compare the total, the elapsed time, GPU case is 2 times faster than CPU case in these simulations. Okay, so first part, the conclusion, GKNet has been implemented on GPU machine by NVIDIA Japan. And total performance is roughly 2 times better than that on CPU. And gyropad like 4.7 times faster than that on CPU of Marconi. Some parts become slower on GPU, such as communication paths and so on. It should be implemented in future. It is left for future work. Okay, so I will move to the second topics. Second topics, this part is done by myself, and this is the failure case. So benchmark environment is, I use 3 environments. One is SGI A600. This is just recently start to operate in JEA and QST supercomputers. And this computer provide the CPU Intel Xeon Gold 624R and GPU NVIDIA V100. So this part is the same to Marconi 100. However, the memory is like a GDX 32 gigabyte times 4. And also we use the JFRS1. This is Intel Xeon Gold, and the Marconi 100 is like this. And this is the firstly, I use this SGI H600, and compiler we use first case the Intel compiler case, and second case this PGI compilers to compare the CPU benchmark for these 2 compilers. And this is a result of this the code. And you can see this Intel compiler plus MKR case compared to OpenBRUS plus FFTW. Here, this subroutine TM left-hand side. Actually, this subroutine we use FFTW and TM push. This subroutine we use LAPACK functions. And if you compare these 2 results, you can see this TM push. It's this MKR LAPACK is very fast compared to this OpenBRUS. And so this part is bottleneck of this code. And roughly Intel compiler and MKR is 3 times faster than PGI compiler plus OpenBRUS and FFTW. And secondly, I compare to this CPU benchmark result, this new machine, and JFRS1. And in JFRS1 case, we use a Cray compiler plus MKL. And you can see the almost the total elapsed time is similar to this SGI H600 and this Cray JFRS1. The SGI machine is recently installed, and I think this the CPU capability is better than the old the Cray machines. And even though these 2 compared to this the 32 process on the 64 process cases almost same. Even sometimes JFRS1 is faster. And if we use 128 processes, maybe in this case, this gather subroutine gather user communications, and a little better than this the hypercube. This is essentially 4 times EDR. Show the better performance than Aries interconnect. this is Dragonfly. But almost these two machines is the same result. And here we just investigate the cost. And for 32 processes case, this TM left-hand side, this take 1,302 seconds. And in this, the elapsed time, the heavy part is one is FFT parts, other is calculation parts. And firstly, we try to use this cuFFT on GPU machines. And also maybe we can apply this, the OpenACC directives or loops in this calc part. And this TM push, we use this Linpack function, the GBSV. This is block bounded matrix solvers. And I searched to some, the alternative subroutine on GPU. However, I couldn't find. So they provide a CU solver. However, this CU solver doesn't support this, the Linpack functions. So we just give up to implementation on these subroutines and only just concentrate this TM left-hand side in this time. And so this is offload of FFT in TM left-hand side. So the difference, this, the FFTW and this cuFFT, cuFFT case, we need to change it to argument like this. But other part is almost similar. And this is a result. And so the first case, this is only the CPU case using MKL. And the middle parts, it's we use a GPU like this. And also they try to compare to Marconi 100 cases. So firstly, we compare TM left-hand side. So elapsed time, you can see cuFFT in Marconi 100 is roughly 1.5 times slower than that in SGI. It's 600 here, middle and this right columns. However, if we compare this Linpack routine like TM push, you can see this part 2.8 times faster than that in SGI 600. And of course, total, the elapsed time is 2 times faster than SGI cases. Next, we simply they insert some simple directives like this. So there are some loops in calc, and just simple loop vectorizations using OpenACC. And so this is just the compile options, and we have some information too. If without OpenACC case and with the OpenACC case, this elapsed times take a longer with the OpenACC case, so it becomes worse. Okay, so this is the conclusions. Benchmark test of Schu's spectral code R5F is performed on GPU machines. This code uses FFTW and Linpack ZGBSV functions via MKL libraries. And these two parts is the heavy part in this code. And FFTW in TM left-hand side is replaced by cuFFT. However, the performance becomes worse because this, MKL tune pretty good for, this Linpack and FFTW. And do loop is also parallelizing using OpenSCC. However, performance becomes worse. Maybe we need masking the communication between CPU and GPU might be necessary to improve the performance. This actually done in first example like a GKNet, NVIDIA Japan done such masking communication. And this technique also should be introduced for loop vectorizations. In any case, it will take a time to optimize the code on GPU, and it is left for future work, especially Linpack function should be. That's all. Thank you for your attention.
Thank you very much, Masatoshi-san, for your talk. Any question for Masatoshi-san? Okay, so I see no question. Okay, again, thank you very much for your talk and results presented. I think it was definitely useful. So we are clearly ahead in the timeline, but let's say it's quite a good news. Better to be ahead than late. So the next point is, if you want to, there is an open discussion and question if you want to exchange on a specific point. So on my side, I'd say that regarding your talk, Masatoshi-san, we're still, and all your talk actually, we're still kind of stuck in this problem of portability versus performance. Masatoshi-san, what would you say? What would be your priority? Would it be portability? Would you prefer degrading lower performance and make sure your code is portable? Or would you take the other way around?
Yeah, probably, GPU, like the standard user use like a Linpack or such open source libraries, and MKL provide a pretty good performance. So if GPU, the NVIDIA provides such the alternatives, maybe we can use on GPU. However, the present the case, maybe we need to implement everything on GPU, even this Linpack or FFT or the write by ourselves. Otherwise, the code not good performance. This is an essential program for normal users, I guess.
Thank you, Masatoshi-san. Any other reaction?
Yes, I have one comment to Masatoshi-san. I saw that you programming and port on GPU using OpenACC. Did you consider it to make it more flexible with OpenMP 4.5 or 5.0?
Yeah, actually, my code is like a hybrid code. So already I use OpenMP parts indirectly in the code, actually. But so far I didn't try to use OpenMP 5.0 or something.
Another comment from my side to all of the speakers regarding the presentation you made. Is there any option to explore machine learning to create new model to replace some part of the simulation or to complete the simulation, post-processing, pre-processing? So the silence means no, I guess. Okay, so do you any other point you would like to address? Okay, so I propose that we moved in the agenda. So the next point is you, Richard. I see. Maybe Jacques. Maybe you try to speak with. Okay.
Yes,
yeah.
yes. I had a question, a general question for those that try to use GPU. Did you try to have smaller precision, like 32 bits or something like that? Because accelerators are much better with GPU, are much better with 32 bits or even less. I know it means verification of influence of the reduced precision, but in some place you could get better acceleration. So was wondering if you had a look at that.
I can tell you what we have done in OP5, which is that we have not reduced the precision for the calculations. I mean, there's a reason why on a CPU we want to use double precision. And at least to start off with, we're being conservative with that on the GPU. On the other hand, there are certain sets of information which are being carried around only for the purpose of diagnostics. And so in our PIC code, we have certain attributes for each marker, and some of these attributes are used only for diagnostic purposes. And these have been reduced in precision simply to say, so that's from the point of view of saving total memory capacity, which of course is very limited on a lot of these GPUs, rather than necessarily because the reduced floating point performance on the accelerators.
Thank you, Thomas and Jacques. Any other point? Okay, so let's move to the next point. So Richard, it's your turn to talk, and I invite you to make the conclusion and close of this workshop.
Okay. Okay, so thank you, France, for giving me the floor. And again, good afternoon to all our friends and colleagues in Japan, and good morning to all our friends and colleagues in the EU. I wish to thank you first for taking part into this workshop. As you noted, this is a workshop that is within the collaboration between Japan and the EU, and that's the context of the broader approach. And we have set up everything so that we could maintain dialogue in terms of what is going on the HPC, say, horizon, and also share the good practices and experience. In particular, in this case, the idea was to try to together boost the usage of GPUs within our community. As you know, GPUs are coming stronger on the market, and there is the expectation that within a reasonable short future, we as a community of HPC users, we could be faced with the need and the obligation to transit immediately to the GPU architecture, because there will be very little alternative provided. So that's the reason why within this context, we have been providing, in the EU at least, resources to our Japanese colleagues and friends to access the M100 platform, which is a GPU platform that we have within the EU, so that we can together explore our experiences on using this for our specific homemade codes. And I would like to praise the effort put on both sides, in Japan and in the EU, for making this possible, and in particular for organizing this workshop today. Thank you, France, a lot for bringing together around the table all these very nice speakers. And thank you to the speakers for going to the effort of selecting some of the work you have done in the recent past and sharing it with us, so that we can get a better understanding of what you have been doing and what is the kind of experience and knowledge we gain from that. This is very useful, I think, and this is the spirit we like to maintain that is to share experience and best practices as much as we can. And I think we can say today the workshop has been a success, is a success in that, or in those terms, let's say. And what I also would like to say is that although the workshop is a good platform for doing this, we also intend to, everywhere possible, maintain exchanges. That means, if anybody has any question or wants to know whatever at any moment in time, you may not need to wait for the next workshop. You can just approach anyone here, and if there is a possibility to do so, the help will be provided at any moment in time. You can address speakers, you can address one of the organizers, if not all of them, and I think everybody will be happy to contribute to addressing your issue, your problem, and contributing to the furtherance of your work. I think this is all I wanted to say, and I guess that, as we typically say, we say that collaboration is a trademark of fusion research, and this is what we experience today. So we keep being very, very, very close to this idea that we need each other to progress, we need each other to move forward, and I think the future will only demonstrate that furthermore. So thank you all again, and I wish you a very good day. And I guess, Franz, you may have additional comments to make in terms of what will be happening with the materials that was presented and so forth. So I hand over the floor back to you.
Thank you, Richard. So indeed, this workshop is recorded, and I can stop the record actually.